Today we are going to discuss about the asymmetric synthesis topic. This topic belongs to Chemistry 5 Block 3 BSc third year. It is also covers a part of Block 3 Course 6 MSc Chemistry also. Now coming to the topic asymmetric synthesis. To explain these topics, we have two eminent personalities are with us. In that, Dr. J. Mohan Babu, University College of Science, Saifabad. Dr. M.D. Arif, he is the senior faculty member, expert in JEE mains. Now coming to the topic, asymmetric synthesis. What is asymmetric synthesis? What is its significance? What is the need to we learn that topic? First we coming to the asymmetric synthesis. What is the asymmetric synthesis? Please understand that without understanding of topicity, and that means what is the homomorphic nature of the ligands or homomorphic nature of units, based on that we are classifying the ligands or units in the within the molecules are homomorphic ligands, homomorphic phases or homotopic phases, or heterotopic ligands or heterotopic phases. Based on that we can understand the asymmetric reaction. Then only we can decide whether the reaction is moving asymmetric way or not. Okay. Now whenever we are conducting the asymmetric synthesis, asymmetric reaction, the substrate is an important aspect for the reaction. The substrate sometimes chiral, but most of the cases that is the achiral. That achiral compound is transformed to chiral compound after the reaction. Okay. When you consider that substrate, achiral substrate, that is converting from achiral to chiral. Okay. Now I am asking Dr. Arif, that substrate is converting achiral to chiral, then what we call it as? Suppose if you are assigning some notations to that substrate, how we are going to assign it?
Yeah, sure. So first of all, let us discuss about prochirality. So before prochirality, we should understand about what do you mean by prochiral molecule, right? So I'm taking this typical example which is called propanoic acid. So these both are two hydrogen atoms, and this is the carboxylic acid and this is the methyl group. Now is it a chiral molecule? It's not a chiral molecule, but if I will replace one of the hydrogen with any one hydroxy group or anything, it will become a chiral. Then this molecule is called prochiral molecule. It is called prochiral molecule, or else it is also called prostereogenic molecule. So simply we can say that prochiral molecule is nothing but which is a substrate of a chiral molecule. If you replace one of the atom from the prochiral molecule, you will get the chiral molecules, right? So this is a way of synthesizing the chiral molecules from the prochiral molecules, and this phenomenon is called prochirality. And if you see in propanoic acid, we have three kinds of hydrogen atoms. One hydrogen is present at carboxylic acid. Now 3 hydrogens are present at methyl group, and 2 hydrogen atoms are present at alpha position of the propanoic acid. And these three hydrogen atoms, actually these are three different set of hydrogen atoms. If you see methyl group, 3 hydrogen atoms are called homotopic ligands, because if you replace them you will get the homomers. But especially there is a alpha hydrogen atoms are there, right? They will play a very significant role. Why? Because these are enantiotopic ligands. Now what I am doing is, if I will replace one of the hydrogen atom, which is these 2 hydrogens are close to the observer, if you are the observer, right? So that's why we are placing these 2 hydrogen atoms in a horizontal plane. And if you see this carboxylic acid and methyl group, they are away from the observer. So because of that we are placing them in a vertical plane. So what I will do is, I will replace one of the hydrogen atom. Just for our convenience, what we are doing is, we are just labeling it as a HA and HB, right? These both are enantiotopic ligands. Why? Because if I replace HA, I will get one isomer, it is D. If I replace another one HB, if I replace the HB, what will happen? I will get a L isomer. So this D isomer and L isomer of this lactic acid, it is called lactic acid after replacing with a hydrogen atom with the hydroxide group. And if you see this D and L, both are non-superimposable mirror images, so these are called enantiomers. So if I replace these 2 hydrogen atoms, in such cases I am getting the enantiomers, right? So that's why these hydrogen atoms are called enantiotopic ligands. And whatever the chiral center which is going to generate, so this chiral center is called pro-chiral center, but actually it is not a chiral center. If I will replace one of the hydrogen, I am getting the chiral center, right? So this is the substrate of my chiral center, so that's why this chiral center is called pro-chiral center, and this molecule is called pro-chiral molecule. So this is called pro-chirality. So whenever we are synthesizing, these all chiral molecules are very important. Why? Because all the naturally occurring molecules are chiral molecules. So when we are replicating these all molecules in the laboratory, so in order to study them, it is very important to know, define some symbols, right? So these symbols we will assign for only enantiomers and diastereomers. Enantiomers generally we will study by using RS nomenclature, diastereomers like cis we have, trans we have, and EZ nomenclature. These nomenclature we will use for the study of diastereomers, right? So what I am doing is I am taking this again propanoic acid. So this propanoic acid, this is methyl group, this is OH, right? If I will replace one of the hydrogen, I am getting the S isomer. If I am replacing one of the hydrogen, if I am getting the S isomer, now this hydrogen atom is called pro-S. If I am replacing these hydrogen atom, then if I am getting the R molecule, in such cases this pro-chiral molecule we will give it as a pro-S. So generally R and S nomenclature we will use for normal chiral molecules, and pro-R and pro-S we will use for the pro-chiral molecule, which is going to convert it into the chiral molecule, right? So this is in chiral system how you will give the nomenclature of pro-R and pro-S. Same way in double bonded system also we can do, right? So if you are replacing any one of the hydrogen atom, if you are getting the E configuration, then that is called pro-E, or else for example this is the double bond, right? It is also have a two phases. So if a nucleophile, if a electrophile is attacking from the top phase, we will call it as a C phase. If it is attacking from the bottom phase, we will call it as a Re phase, right? So there are certain methods to define, to give the nomenclature of these chiral molecules and diastereomers. So let us see. In that first method is called Hansen method. So this Hansen method, what it will do is, so just we are classifying for our convenience these ligands, and here top and bottom, which is away from the observer, two ligands are there, right? So these are called paired ligands, and horizontal line which are close to the observer, these are called unpaired ligand atoms. So you can replace these, unpaired ligands. So what Hansen method suggests that whatever the unpaired electrons, always you should, whatever the unpaired atoms are present, right, these all unpaired atoms you should arrange in a horizontal manner, right? This in Fisher they will come horizontal, right? Matlab whatever the unpaired ligands are there, they should arrange in a close to the observer, and what are the paired ligands which we are not going to disturb, them. So these are called paired ligands. One is OH and CH3. They should be arranged in a vertical plane. They should be arranged in a, away from the observer, they should be arranged in a vertical column, right? So this is only Hansen method. Unpaired ligands arranged in a horizontal line, and paired ligands arranged in a vertical line. Now what I will do is, in order to give whether it is pro-R or pro-S, these are hydrogen atom, right? So as we know EZ nomenclature, as we know CIP rules, Korn-Ingold-Prelog terminology. So what I will do is, if you have a hydrogen atoms, you can't tell whether it is R or S. Why? Because both hydrogen atoms are same, they have a same atomic number, they have a same atomic masses. So CIP will not work. So what I will do is, I will replace one of the hydrogen atom with the deuterium atom. Let us consider that this is our deuterium atom, right? So I have replaced. Now after replacing this one of the hydrogen atom with the deuterium, what now I can assign RS nomenclature. Why? RS nomenclature, CIP rules suggest that first we should check the atomic number. If atomic number is same, in such cases we will check the atomic masses. Hydrogen and deuterium have a different atomic masses. So because of that, now we will give the nomenclature to this, and what we will call it as, whenever we are giving the RS nomenclature, so this is a methyl group, this is the COOH group. First you should give the priority to the OH group, after that we should give the priority to the COOH group, after that methyl, after that hydrogen. So after replacing one of the hydrogen with a deuterium, if I am getting R, in such cases this hydrogen atom is called pro-R center. So if I replace another one hydrogen atom with the heavy atom, and if I will give the RS nomenclature, if I am getting the S, then that molecule, that hydrogen atom is called pro-S. This is your Hansen's method. So simple Hansen's method, you should keep all unpaired ligands in a horizontal manner, that is close to the observer, and paired ligands you should place in a vertical line in a Fisher projection which are away from the observer. In the same way, we have another one method which is called Nasipuris method. So in Nasipuris method, what he will do is, these are unpaired ligands, right? Let us consider that this is the OH, this is the methyl. According to the CIP, which is the first priority we will give? OH will give the first priority and methyl we will give the second priority. So in paired ligands, so top priority in a CIP I am placing at top.
Right.
So that's why this is called top. Now let us discuss about the unpaired ligands. So in unpaired ligands, if I replace one of the hydrogen with the deuterium, if I am placing that hydrogen atom, I am placing right side hydrogen atom with a heavy atom. In such cases, that is called right. So overall, in unpaired ligands, top priority is at top. In horizontal line, the top priority is right. So this classification is called top right. Same way you can keep it as a top and left also. Now another one method is, now this is the top priority, right? I am inverting this molecule like this. I am inverting the molecule like this. Now our top priority changes into the bottom, right? Now this is the bottom, and initially which is at right side, the top priority which is at right side, that is coming to the left side. So this way of representation is called bottom left. So there are two ways. Typically, if you are keeping your unpaired ligands at the top, then that is called top priority, and horizontal line if you are keeping it right, that is called top right. So top right, top left. In the same way, you can also keep high priority group unpaired ligands at the right side, and in hydrogen atom you are replacing to the top one, then you can call it as a right and top, and also we have a left and top, and same way you can write right bottom and left bottom. So these are the few prochiral symbols. So another one is, now let us this is for the typical CH4 molecule. Let us see acetaldehyde. So in acetaldehyde, this hydrogen atom, in formaldehyde I am replacing one of the hydrogen atom with the methyl group. Now these two hydrogen and methyl, these are different, right? So generally this C double bond O group, carbon and oxygen is the more electronegative, so it will takes the electron, carbon will get the positive charge, right? So they are very susceptible towards the nucleophile. Now the incoming nucleophile, when I am placing like this molecule, the incoming nucleophile, it may be attacked from the top face, it may be attacked from the bottom face. Yes or not? There are two choices. If it will attack from the top face, I will get one isomer. If it is attacking from the bottom face, these are you will get another one isomer. Matlab these two isomers, they have a different properties. You are getting the enantiomers, right? They may have a same physical properties, but the chemical properties are different. So the properties of the molecules also different, right? So if you are attacking from the top side, right, that phase is called re phase. If it is that phase is called C phase. If you are attacking from the molecule, matlab you are viewing the molecule from the bottom and the nucleophile is attacking from the bottom side, then that attack is called re phase attack. If it is attacking from the top side, that attack is called C phase. So this is, if you are generating an enantiomer, then only we will call it as a C phase and re phase. If it is generating the diastereomers, then the classification will be different, right? So whenever after attacking, if you are getting the enantiomer, if it is attacking from the top phase, that is called C phase. If it is attacking from the bottom phase, that is called re phase. This is for enantiomers classification. Same way you can classify for the diastereomers also. You can see in the screen. So there is a C double bond O group, right? So we have a tertiary alkyl group which is present at equatorial position, and the incoming nucleophile, it may be attacked from the top phase, it may be attacked from the bottom phase. Initially earlier we saw that if it is attacking the top phase, we said that it is a C phase, right? But in diastereomers it will be reversed. If it is attacking from the top phase, that is called re phase. If it is attacking from the bottom phase, that is called C phase. So here also you will get two different isomers. Earlier cases we got the enantiomers which have a same physical properties and different chemical properties, but this time we got diastereomers. Which have a different physical and chemical properties which are non-superimposable, non-mirror images. So this is about classification of re phase, C phase, and everything, prochirality.
Yes.
And let us, that's all about the prochirality.
Arif, you are explained about the substrate molecule as prochirals. Okay. Yeah. When these prochiral molecules are converting into stereoisomers like enantiomers and diastereomers, in the asymmetric synthesis means one of the particular isomer is the major, one of the when you compare to the its counterpart, right? Suppose if the enantiomers are there, E1 and E2 are there, E1 is the major when you compare to the E2, right? How these formation takes place, what we call it as.
Yeah. See, whenever a prochiral molecule is changing into the chiral molecule, we have a different set of reactions. There are few reactions are there, you will get only one product. So, there is a one prochiral A, just call it as a. After reaction, you will get only one molecule which is B. Then typically those are called stereospecific reactions. So, there is no problem in that reaction. But there are few reactions. There is a high chance of there is a multiple pathways, not only one path. If you have a one path, you will get only one product, right? But there are few reactions we have a multiple paths. Then such kind of reactions are called stereoselective reactions. Yes. So in stereoselective reaction, you will not get one product. 100% if you are getting one product, there is no problem. But in stereoselective reactions, what will happen is you will get more than one product. You will get more than one product. One may be E, another one may be Z. The best example is EZ. Best example is E2 reaction. So if you see in E2 reaction, which is located in your screen, in E2 reaction there is a chance of getting the two products, yes or not. One is a major product, another one is minor product. So whenever there are multiple possibilities are there, but the reaction is choosing only one path to get the high percentage of the product. Major matlab around 70 to 80% you will get major product, and rest of the percentage is minor. You can see in this Newman projection formula. So in first formula, it is a very stable conformer which is leads to the trans product. The second conformer, there is ethyl are adjacent with each other. There is a van der Waals interactions are there, which are also called steric repulsions. So the resultant product is a cis. So that's why the cis percentage is very less than compared to the trans percentage. So understanding stereoselectivity, one of the best example is E2 mechanism. Right, you are getting the two product, one is major, another one is minor. What is the reason? Because if you see in the transition state where the baby alkene is forming, right, in transition state when minor product is forming, there are high repulsions. So that's why the alkene yield is less. But when the major product is forming, the baby alkene, when it is forming in the transition state, their repulsions are very less. So because of that, we are getting the high yield of the product. So stereoselectivity is depends on the reaction path, how it is traveling. So this is about stereoselectivity. And also you can classify the stereoselectivity into the different paths while doing the asymmetric synthesis. One is stereoselective substrate selectivity and product selectivity, and again substrate selectivity also classified into different ways, and product selectivity also classified into different ways where we are getting enantiomers, diastereomers and everything. Now let us see substrate stereoselective reactions. A very simple example is what is the use of this substrate selective reactions is, for example, you have a two isomers, say A and B. A and B I am using. So I am using another one reagent which is a chiral. A and B are chiral, and also I am using C reagent which is chiral. Now C will react with A and it will form AC, and C react with B and it will form AB. And this AC and AB should be diastereomers. Then you can differentiate the AB. If A is plus, B is minus, and C is plus. Now plus plus you will get one isomer, plus minus you will get one isomer. This plus plus and plus minus are diastereomers. So these are non-superimposable, non-mirror images, diastereomers, and these diastereomers have a different physical properties. So on a diastereomeric environment, you can differentiate the on diastereomeric environment you can differentiate the enantiomers. So that is called substrate enantioselectivity, and earlier slide you can see many examples also. So that is called substrate stereoselective reactions. And let us see substrate diastereoselective reactions. So on screen you can see there are two isomers, one is Z-acetophenone oxide, another one is E-acetophenone oxide. Z and E are, these are generally diastereomers, and both are undergoing Beckmann condensation, Beckmann reaction. So due to that Beckmann reaction, what is happening, H plus is going to water and it is removing the water, and the group which is opposite to the OH, the methyl group is migrating. As a result we are getting N substituted methyl. In second reaction also Beckmann reaction is going on, and as a result we are getting N-phenyl acetonylide. So we are getting two different kinds of the reaction, right? This is called substrate diastereoselectivity. So that's all. This is about substrate enantioselectivity and diastereoselectivity. That's all. Thank you.
Now I am asking the continuation. What is product stereoselectivity, Mohan sir?
Yeah. So here the selectivity is very important in the asymmetric synthesis. So generally here the product stereoselectivity reactions, that means one substrate molecule when it is forming the two unequal products, unequal percentage of products or exclusive one product is called the product stereoselective reactions here. That means here for example A gives the B plus C. Okay, A is a substrate compound here where it is going to form the two products like B and C here with a different ratio of the percentage here, like B is a 95% and C is a 5% here, or sometimes what happens here, A gives only B with 100% product here. So generally we call this is the asymmetric synthesis only, and stereoselective synthesis. Okay, and the point to be noted that here all the asymmetric synthesis reactions are stereoselective synthesis reactions,
Yes,
but
100%.
not vice versa.
Yes.
Means all the stereoselective synthesis reactions are not asymmetric synthesis reactions here. Okay, means all the asymmetric synthesis, okay, all the asymmetric synthesis are not stereoselective. Okay, so this is the very important thing to be observed here. Now we will see the in this particular product stereoselective reactions. Again we have classified into two types. One is a product enantioselective selectivity and product dash stereoselectivity here. So product enantioselectivity means where that particular the chiral reagent or the achiral. So the reagent it may be chiral or the achiral here. When it is choosing the one of the isomers, one of the enantiomer to give the product, right, stereoselective product, we call the product enantioselective reactions here. Here we will see one example like on this particular reaction where here the glycerol when it is reacted with the ATP, okay, this is the reagent ATP, so adenosine triphosphate. So when it is undergoing the phosphorylation reaction, so among the R and S configuration, so this ATP only phosphorylated with R configuration. That means exclusively it is choosing R configuration to get the phosphorylation here. So it is not reacting with the S configuration. Yes. So it is selective towards its right reactant here. And another example, if you see this particular ethyl methyl malonic acid, this is particular brucine. So brucine is a natural product. Yes. Okay, so it is undergoing the decarboxylation reaction and it is going to form the this particular S2 methyl butanoic acid as a major product here. Yes. Okay, so it is choosing the only S isomer only, but not it is the decarboxylation is not taking place in the R isomer. So this is selective towards its substrate here. That means the reagents, okay, the reagents are selective towards its substrate. Yes. And it is going to form the exclusive product.
The substrate is racemate you are taking.
Yes. Now the enantio phase differentiation reactions. Okay, there is a enantio enantiotopos
ligand
differentiation means ligand based. Here the phase means you can say that the phase, whenever you see the phase, that means it is in the sp unsaturation. Okay, sp2 hybridization here, like carbonyl compounds or the olefinic nature. Yes. Here. Okay, so here also we will take this particular phenyl isopropyl ketone. So this particular Grignard reagent, right? Yes. This is the chiral in nature. Yes. This Grignard reagent. So it is going to attack on this particular carbonyl compound. So it have the two choices, like it may be attack from the top phase or the bottom phase here, but here it chooses the sterically less crowded center here. Okay, so for example when it is attacking from the top phase where the bulky phenyl group is there, so this methyl particular Grignard reagent, it does not attack from the top phase because due to the steric hindrance of this phenyl group here. So by chance it may be attacked from the bottom phase only, because the isopropyl group it is not much bulkier than the phenyl group here. So, it may be attacked from the bottom phase, and it leads to formation of this particular intermediate compound, and finally by hydrolysis it is giving yes 1-phenyl 2-methyl propanol alcohol product here. Okay. So, this chiral reagent is selective towards this particular carbonyl compound here. This is the diastereomeric reaction here. Next, one more example we can see with this particular diastereo selectivity, right. So, where this multi-chiral center compound, okay, this multi-chiral center compound, when we are it is having the diastereo hydrogens here. Okay, we will see this compound generally it is not a it have two chiral center generally, one is chiral center, another is a pro-chiral center, okay, because it is having two hydrogens. So, it is not a chiral nature, it is pro-chiral center, and this is the chiral center here. So, here this pro-chiral center is having the two hydrogens, okay, with labeled the stereo pro-stereochemistry like HRR, and here is a HSR, HRR, HSR. So, these are the pro-chirality symbols here, okay, as the Arifs are explained. Okay. So, we have two options here. Now, in the elimination reaction, okay, so in the elimination reaction you can see in this Sahar's formula. So, where the HRR ligand is going to eliminated as hydrogen bromide here, and it is going to form the trans-stilbene product. Okay. So, it is selective. Okay. So, whatever the reagent, this particular nucleophile, it is abstracting this particular HRR ligand, and it is leading to formation of a trans derivative here. Okay. This is product diastereo selectivity.
In the entire session of this topic discussion, asymmetric synthesis, we known about the homomorphic units. Based isolation of the atoms or groups from the molecules, we understand the homomorphic units. Based on the homomorphic units, we are classify the that units into ligands, homotopic ligands or homotopic phases, and later some of them are classified into heterotopic units, that is heterotopic ligands at heterotopic phases. Based on that, we are classifying the substrate into prochiral molecule. That prochiral molecule, after formation of the product, how that prochiral molecule is arranged at the prochiral center, that is a pro R, pro S, or rephase, psi-phase for the phases. Based on that, we are conducting the reaction. The conducting of reaction is also, that is called selectivity. Based on the selectivity, again the reactions are classified into substrate stereoselectivity and product stereoselectivity. That substrate selectivity is also enantiotopic stereoselectivity and diastereotopic stereoselectivity, that is substrate stereoselectivity, and products based on the product formation, product stereoselectivity is classified into 4 types. This entire we are discussed, and in the entire this topic is further continues. We need to characterize or calculate the proportion of the or composition of the isomers formed in the reaction, that is expressed in terms of enantiomeric excess and diastereomeric excess. After characterization, we are also studied about the strategies of asymmetric synthesis, first generation strategy, second generation strategy, third generation strategy, and fourth generation. The first generation is substrate control, second generation is auxiliary control, third one is reagent control, and fourth one is catalyst control. Okay, this is called asymmetric synthesis entire topic. This is very helpful to you. Thank you.